everyone, my name is Nalan. I'm here to give my project presentation. So my project basically involves working with a mobile manipulator, and the reason why I chose this manipulator was because of the ease with which it works with humans. My motivation, it started specifically at construction sites. So tasks like pulling out a wrench from a shelf can be sometimes dangerous because you work with various other tools, dangerous tools like power drills, nail guns, saws, etc. Also, we have some repetitive tasks like, for example, pinning down 100 nails on a block of wood, which can be sometimes tedious for humans, and that's why I chose this robot, which can actually make this process much easier. So this is how the robot looks like. It has a mobile base, which is manufactured by ClearPath Robotics, and we have a UR5 cobot arm. This is 6 degrees of freedom arm, and it's mounted on this, and it's actually manufactured by Universal Robots. And here are the specifications, as you can see. Okay, so the objectives of the project basically is to model the forward kinematics and inverse kinematics of the manipulator arm, navigate from start point to a certain toolkit shelf in a room in a construction site, pick up a wrench from the shelf, navigate to another part of the room and place the wrench on a bolt head, turn the wrench to tighten the bolt, and model the velocity kinematics for the robot. Wow, that seems like a lot. Okay. So the tools used are basically Gazebo, Arvis, Move It, MATLAB, Linux, ROS, just standard stuff, Then we have the forward kinematics. So this is basically the zero configuration of the robot arm. So here I have basically the my final transformation matrix. I've just plugged in the values. I got the translation values and the rotation values. As you can see, these translation values match with the translation values given by the RVS. And also I just converted my rotation matrix into a quaternion form because the RVS also gives it in this form. So I just did this for 3 configurations, and it got validated. Also for inverse kinematics, I'm just actually I'm in the process of doing it because it has a spherical rest. So the calculations can be challenging. I'm using the geometric approach. I'll be deriving joint variable equations and basically choosing 3 end effector poses, plugging them into the equations, then plug in the derived joint values into RVS and basically see where the end effector pose is and just verify that with my initial end effector pose. And that validates my inverse kinematics. So this is my velocity kinematics. I just derived the Jacobian matrix, equations for the linear angular velocities, then plug my 3 joint variables into the union joint velocities equations, and basically do the same thing for the simulator. And if the velocities are matching, then my velocity kinematics is validated. I'm also doing motion planning wherein I'm using Move It, and this is for the robot the arm to actually reach the shelf and pick up the wrench. And I'm using Open Motion Plan Library. I just implemented an algorithm here, and this is basically a path planning which I'll be doing. So here, basically the robot has to navigate from point A to a certain toolkit shelf, and for that I've just devised a small controller in which you just give the goal coordinates, and yes, the robot goes from point A to point B. Things to work on from here: spawn the robot in the construction site. Now I'm in Gazebo. We work the controller to add waypoints for the robot to navigate to, basically make a path. Then add an appropriate gripper to the end of the arm for picking up the wrench, and then work on the grasping problem. So yeah, any questions? Thank you.